But the key thing is at this point, I change it to an exponential, and then it should feel so much friendlier, right? 3 cubed, which is 27, equals x squared plus 6x. So now it's like an algebra 1 quadratic that we're going to solve. Again, when my leading coefficient is a 1, I don't need a diamond. I just need to look at it and say, hey, what two numbers multiply to give me negative 27 and add up to positive 6. So you correctly factored it as x plus 9 times x minus 3. So then you've got your answers being x using zero product property. My answers are x equals negative 9 and 3. But super important, don't forget this last step. I need to make sure that both of those numbers work in my original equation. I can't take the log of negative 9 or negative 3, right? If it's not feeling that way now, hopefully like maybe by the end of the week, right? Oh no, I can't take the log of 0 or a negative number, right? It kind of blows up, right? So that's why you have to cross that negative 9 out. It is extraneous, okay? So then this one, you can actually, it's easy to do in your head and see that it works, right? I put in my x being 3, log base 3 of 9. Well, that's 2. Log base 3 of 3, that's 1. 2 plus 1. Like that one, it's easy to just put it in and you can just tell, easily that it works. Okay, for number 3, the key was remembering that, oh, I could rewrite that 81. So remember on the page 12 of notes, 3 to the 4th is 81. If you did that, it made this a lot easier because then if I've got the same base, I can just pull the two exponent pieces out and just look at those. And so now, very friendly, 2x minus 4 equals 4. I solve that and I get x equals 4. Again, this one's super easy to drop it in. 2 times 4 is 8 minus 4 is 4. And we do know that 3 to the 4th is 81. For number 4, you wanted to take log base 3 of both sides. Okay, the reason you'd want to do that is because then this side's going to be just 2x minus 4. And the other side, okay, you could put it in your calculator and get the decimal approximation, right? But does it make sense? Log base 3 of 5, that's the exact way to say a number. And we know that number is between like 1 and 2, right? Because log base 3 of 3 is 1. Log base 3 of 9 is 2. 5 is a number in between 3 and 9. Okay, so I know it looks a little ugly, but you just kind of have to, it's like maybe like when you were first using pi, you kind of didn't like mixing pi in with numbers. I don't know. So now I'm going to add the 4 to both sides. So again, in first period, there was someone who said, well, do I add the 4 to the 5? And that's no. Remember that the combining like terms problem, this one. Right? Remember how this problem kind of that you had to keep these as separate terms, kind of the same thing here. The separate terms divide by 2. Okay, if we are doing a no calculator assessment or no calculator problems, you're good at this point. That's the exact answer. That's beautiful. Then if you put it into your calculator and you got the decimal approximation, then did you drop it back in and make sure it works? Because it's kind of fun. You can then take that value, multiply it by 2, subtract 4, and raise 3 to that power, and you'll get 5. So I don't know, it's kind of a satisfying thing. Get this answer, drop it back in, and verify it works. Something very important. You're going to do both the review and the Unit 8 assessment, no calculator. So that means you're going to stop here. So if you look at this opener, right, except for the switching to the decimal approximation, right, this is a no calculator opener. Okay, so the review, so please do the review without a calculator because it's kind of silly. You do the review with a calculator, the assessment is no calculator. And on that same line, so even if you checked out the calculator out of the library, you can bring it back to me. So Tuesday, extra credit opportunity. Bring your book and your calculator home to school, the home of the book. And then you get the extra credit points. Okay, so Tuesday, put a note by your door. I'll send you a reminder. Booking calculator, coming home to Archie Williams on Tuesday. Okay, because we won't. So you definitely want to use your calculator to finish up this assignment before I see you Tuesday, because you're turning it in. Then you have a book though. Yeah, you get the same extra credit. So for the people who are just book, you get the same extra credit as people returning book and calculator. Okay. Pardon? The book, it looks like this. It's the big book, right? Okay. No.
It's got a spiral.
This is the book. Okay. It is a problem if you've done the whole year with no book, but okay. So okay, so hopefully I now have had time to do page 14, right? Kind of read through that problem. Okay, so this is taking, this cough medicine, and it has a half-life. So there's a lot of things that have a half-life, right? Caffeine has a half-life, right? So many hours after you've had a cup of coffee, it's still in your system. There's also things with a half-life like plutonium, uranium, radioactive, elements. Their half-lives are really, really long, right? So some things can have a half-life of a few hours, even sometimes minutes, right? Or a half-life can be days or weeks or years or hundreds of thousands of years. So that it's all about they'll tell you what the half-life is. And if you know the half-life, then you can calculate how much is going to be left of this material for any other point in time. Okay. So in this story, they told me it had a half-life of 3 hours. So that means every 3 hours, your body's going to eliminate half of it. There's 30 milliliters in the dosage, but that's not all active ingredient, right? The active ingredient is the 20 milligrams, okay, of the dextromethorphan. I don't know. And after 3 hours, 10 milligrams is going to be in your system. So when they say how many is left after 6 hours, I'm going to say half of 10. So here, if you write it out. So we started with 20 milligrams, right? And after 3 hours, you had 10 milligrams. So then another 3 hours went by. So after 6 hours, now you had 5 milligrams. So then after 9 hours, you had 2.5 milligrams. So hopefully most people had time to read the story and do this first part before we did. Okay, and so then it says how many milligrams of the drug will be in your system after 10 hours. Well, after 9 hours, there's 2.5. We can go another 3 hours, right? And say after 12 hours, there'd be 1.25 milligrams. So to answer this, did people say about 2? That was a reasonable answer, okay? To say about 2 milligrams is going to be, because right after 9 hours, I had 2.5. After 12 hours, I had 1.25. So we didn't, because what we're going to do right now is tell you the best way to calculate this, whereas you didn't necessarily have the best way to calculate this before. You could have done something like, you could have said, I'm going to take the initial amount and then multiply it by a half raised by the time divided by the 3 hour half-life. You could have done that, but I don't think that's the best way to do it. I think the best way to do it is what we're going to do is we're going to use the formula. Okay, we're going to use a formula that says the amount you're going to have after some time is the initial amount multiplied by e to the k times t. So this looks like, right? You're probably saying, right? That looks like that principal times e to the RT, right? Okay, it's very similar. The thing is, this is, right, used with kind of interest rate, money is what we've used. This we're going to use for anything. It's not necessarily increasing. It could also be decreasing. Okay, so we're going to write this d of t equals, and this is my initial amount. So I've got 20 milligrams and e to the kt. So what I know is that I had 10 milligrams left after 3 hours, right? So 10 equals 20 times e to the k times 3, right? If the half-life is 3 hours. So, okay, so this is important that you can figure out what the K is if they tell you the half-life. This is a super common setup. They say the half-life is, and maybe it'll be 3 hours, maybe it'll be 18 months, maybe it's 100,000 years. I mean, depending on what we're talking about. So they'll tell you the setup. You're going to use that information in this equation to figure out your K. Then you can use that K to figure out, oh, well, what if it was like what we're going to do here? Oh, well, then how much was left after 2 hours, after 8 hours, after all these hours that are not even increments of 3, right? It was fine as long as I asked you 3, 6, 9, 12, 15. We didn't really need anything more, right? We could just use that half-life. But if I figure out the K, I can figure out any increment pretty easily. Okay, so that's what we're going to do right now. And this is why we practiced solving those exponential and log equations. Because when I look at this and I am supposed to solve for K, the first thing I'm going to do, you don't have to, but I think it helps if you put that little dot in there to remind you that, okay, if I want to get that e to the k3 by itself, the first thing I do is I divide both sides by 20. And this is for all these half-life problems, you're going to end up with this one side of it being a half. Okay, so now I've got 1/2 equals e to the k times 3. Okay, we're good with that. Now I'm going to take the natural log of both sides. The reason I do that way this side will just be k times 3. Right? So I take the natural log of both sides. So now I've got the natural log of 1/2 equals k times 3. I'm trying to figure out what k is. So I divide both sides by 3. So I want you to do this in your calculator, right? I want you to say, what's the natural log of 1/2 divided by 3? And you should get a negative number, right? Negative 0.23. And this should make sense that when I take the natural log of a number between 0 and 1, it's going to give me a negative, right? Because the natural log of 1 is 0, right? So you get negative numbers and kind of picture that log function, right? How it goes really steep downhill there, that section. So all those places where your y are negative numbers. Okay, we are going to use this a lot. So I want you to store this value and I want you to call it k. So the way we're going to do that, we're going to use this store little stow button, right? I press that. And since this is, we're going to call it k, I'm just going to store it under alpha k, right? Here's my k. So I'm going to store it under alpha k. So now every time I use k, it's going to be negative 0.231049006. Okay, it holds all those decimals. And so here we have a chance to use it right now. Okay, what percent of the drug remains in your body after 1 hour? I can just say, okay, the amount I'm going to have, or the T, I'm just going to make the T 1 hour, is going to be the 20 milligrams I started with.
How do you store this?
Okay, the STO, the STO button, and then alpha. And I mean, like a lot of times I use J because I like that. I mean, you can use whatever letter you want, but we did, just so we're kind of all doing it the same, I did alpha K. Okay, so that times e to the K, and we're going to use our stored K times 1. Okay, so I've got my stored K. I'm going to say 20 times e to the alpha K, because K times 1, I don't really need to write times 1. Okay, you have done it correctly if you got 15.87 milligrams. Okay. And then they said what percent is eliminated. Okay, so if I started with 20, okay, I've got like about 79% left. So about 20% was eliminated in that first hour. Okay. Okay. Any questions? So now we're going to keep using that stored K because to answer these other questions, because this whole page is about this cough medicine. Okay. So the next thing they're saying is that customers are instructed to use the medicine as directed. And for the average adult, it's effective if it's over 8 milligrams, right? So when you took it, you were at 20, right? And then after 3 hours, I'm down to 10. Okay, when I was down to, after 6 hours, I was down to 5, no longer effective. It stopped working as a cough suppressant once it got below 8, right? So what we're going to do is we're going to figure out how often you should take it. So the way I'm going to do that, remember, this is the formula, and we're going to write it in the box too, right? The amount you have after some time is the initial amount times E raised to the KT. So I'm caring about how long does it take to get down to 8 milligrams? That's the question, right? So I want to know how long it takes, and I'm going to use my stored K, right? This is my stored K, and I'm solving for T, right? Solve for T. Okay, so are we good with the setup of this? And this is why it's kind of good to practice these, because it feels a little bit hard to solve for these equations where the thing you're solving for is kind of locked up in the exponent. But that's why the logs are so powerful. They let it kind of unlock it from that exponent. So if I just write it with numbers, it makes it a little easier, right? Take out that milligram. And the first thing I do is divide both sides by 20, right? Because I'm trying to get the E to the KT by itself, right? Now I've got 8/20 equals E to the KT. What am I going to do to both sides so that then it'll just be KT on one side? Beautiful. Okay? Because even though like it feels like it kind of bugs you that, oh, that's that, you know, exact way to write a number, right? Just have to kind of embrace that. Because the other side now is just K times T. So if I am solving, I know what K is, I've got it stored in my calculator. I'm trying to figure out how long it takes to get to the point where you have just 8 milligrams left in your system. So I'm going to divide both sides by my stored K. So what this is going to look like is I'm going to say natural log, and you could have reduced or simplified this, but you don't have to because we're just putting in the calculator at this point. Natural log of 8/20. And that makes sense. It's a number between 0 and 1, that it's a negative number. I am going to divide it by my stored K. So I use that alpha K again. Did you guys get 3.9? Okay, awesome. That means about 4 hours. And that, like, this is an answer that makes sense, right? Because if you kind of go up here, so I got that my T equaled 3.966 hours. So let's say T is approximately 4 hours. So here every 4 hours, right? We're all good that that's probably what the package says. Okay, so now we're going to kind of look at what this does, right, in our system. And so we know that initial dose of the 20 milligrams, we knew we had 10 milligrams, right, left after the 3 hours. So we're going to figure out how much we're going to have after 2 hours, right? Because I'm like, oh, we already figured out 1 hour. We knew 3 hours, but from 8 a.m. to 10 a.m., how much is left after 2 hours? So the way we do that, right, maybe I'll just put it here. The amount I'm going to have after 2 hours is going to be 20 times e to the k times 2, okay? So that's why it's so nice we have this stored, right? 20 times e to the stored k times 2. Is everyone good that this is how I'm going to figure out how much is left of the 20 milligrams after 2 hours? And I get 12.6. So this hopefully makes sense, right? Because I'm like, oh yeah, that makes sense. After 1 hour, remember I had 15.87. Okay, after 2 hours, I'm gonna have 12.6. I know that after 3 hours, I'm gonna have 10. Okay, but how much is gonna be left here after 4 hours? So this is kind of right after 4 hours after the initial dose. I know that it's gonna be pretty close to 8, right? Because that's how we just figured, but let's just put it in and see, because remember, it wasn't exactly 4, it was 3.96, but you were at 8. So let's do the same thing, but put in a time of 4. So I'm saying 20 times e to the stored k times 4. Okay, are we good that we're at like 7.94? Okay, so, oh, but now 4 hours have gone by. So what am I going to do right now? I'm going to take my next dose, right? 4 hours have gone by. So I now take another 20 milligrams. So what's interesting is at this point, I actually now am up to 27.94 milligrams, which is kind of interesting. I'm actually at a higher level than when I took that first dose. So what we're going to do is we're going to kind of continue this out a bit here. So you're with me that this was 2 hours after the first dose, then 4 hours. Okay, do you remember, hey, how much was left from that initial 20 after the 6 hours? 5, right? We're all good that kind of going up to the first question. I could put in my calculator, but I really don't have to. We know that 6 hours later, there's 5 milligrams left. Well, how much of the second dose is left? Are you with me that 12.6 of that second dose? Okay, so now I've got, at this point, I'm okay, I've got 17. Okay, so what happens now, right? Here, this was the 6 hour. Now I am at the 8 hour point, right? So how much is left of the 20 milligrams? Did someone already figure that out? Kind of curious. Let's do that. Okay, 20 times the e to the k times 8. Okay, so there's still 3.15 milligrams left from my initial dose. Meanwhile, I'm on the 4-hour mark with my second dose. So that's 7.94 milligrams. Oh, okay, but now I'm at 8 hours. What am I going to do? I'm taking my third dose, right? Okay, so now I add another 20 milligrams. So it's kind of interesting. At this point, look what you're up to, right? Now I'm at 3.15 plus 7.94 plus 20. Okay, I'm actually now at 31.09 approximately milligrams. So I'm now way above, right, that initial dose. So this is why, you know how sometimes they say things like, don't exceed more than 4 doses in 24 hours. So they kind of put something cautionary there on like the medicine bottle. It's because you've got this situation that if you just keep going, right, every 4 hours, it's kind of building up quite a bit. Yeah, David?
Can't you just put in, instead of like doing
Oh yeah, you could create the new number. Right, you could, but I think it looks kind of interesting to see. I did this intentionally. You could add them together and then go from that point. But I think it's interesting to see how much is left, right? Because like here at the 10-hour mark, right? If I look and see what I've got 20 times e to the k times 10. So that initial dose is down to, now it's like 1.98 or something. So, and that you can kind of just keep adding them up, right? Okay, is that what people got? So about 2. Okay, and then the 7.94 is down to 5. The 20 is at 12.6. So I don't know, I think it's kind of interesting to just see the kind of the numbers continuing like that, but and so I thought that was kind of a fun problem and kind of see how this actually things would stay in your body. Okay, so what we're going to do now is let's fill out our important ideas here. Okay, so the important idea is that you are going to use, and now you kind of like when we first did the E, right? I think then maybe you don't at first see how useful it is. But it's the E, the natural log is very useful for all of these naturally occurring growth and decay situations. And so this is what we're going to use to model this. The amount you have left after some time is the initial amount times E raised to the KT. And that is used to model either continuous growth or decay. And A sub 0 is the initial amount. So whatever we're talking about, right? That's either going to, like, either it's money that's growing or it's caffeine or cough medicine that's decaying, or the uranium radioactivity decaying, something's moving, right? It's either growing or decaying. And K is the rate of growth or decay. Okay, and just like R, this K is going to be a percent written as a decimal, right? Like the R we used. and this is very important, is that if K is greater than 0, we're experiencing growth. If K is less than 0, we're experiencing decay. So when we figured out the K for the cough medicine, and it was a negative number, like once you're kind of familiar with this pattern, you know you're doing it right. Because anything that's getting smaller, decaying, you should have a negative K value. Okay, and then T is the time. And so it's interesting because sometimes the setup is the half-life is, sometimes it's minutes, sometimes it's hours, sometimes it's 100,000 years, just depending on whatever it is that's growing or decaying. Okay. And then you are going to use ln, right, which is the natural log, right, log base E. That is what you are going to use to solve for K or T, right? You can't, they're either going to give you, and the most common way that you're given this kind of problem is they tell you the half-life. So they tell you there's going to be half left after a certain amount of time. From that, you're able to calculate what K is. Then you can use the K to figure out how much is left after all these other times. Or they could just give you the K like they do in this next situation here. They say estimates of the number in millions of US households with digital TVs is given by this formula. Okay, so here's my initial amount. My K is 0.1171. It's positive. The number of digital TVs is growing. And is it increasing or decreasing? It's increasing, right? Because the K is greater than 0, right? So that is growth. But I actually figured it out. I mean, so you don't have to kind of, but I'll just tell you that when T equals 3, we're up to 43.9 million households. When T equals 7, I put these two numbers, right? So 2003, that's T equals 3, 2007 is T equals 7. And when T equals 7, I'm up to 70.2 million households. So we can see it's increasing, right? And one thing that's kind of, this is a really, really common way to set up a problem. And it's the years after 2000. So are you with me that when T equals 0, okay, is the year 2000? Because otherwise my graph's going to look silly if I have to make my graph go out to the X being 2000 before I have any dots on my graph. So that's why a lot of times they do this. They have the TBO times since 2000. So what does the 30.92 represent? That's the 30.92 million households had the digital TVs in the year 2000. That's when time was 0. And the 0.1171 is a 11.71% growth rate. Okay, just like with the interest rate, like the 0.12 interest rate is a 12% growth. So if I've got 0.1171, I could say that's about 11.7% growth rate. So it says, when will the number of US households reach 100 million? Okay, with digital TVs, right? Because that's what we're talking about here. So the way I'm going to do that is I'm solving for the T, right? When, okay? So it's a solve for T, and my setup is 100 equals 30.92 e to the 0.1171 t. Okay, so we're good that we're gonna solve for t. What's the first step? Awesome. And it helps to put that little dot in to remind yourself, right? Because I want to get the e part by itself, so then I'll take natural log. So my first step is divide both sides by 30.92. Now I'll have 100 divided by 30.92 equals e to the 0.1171 times some time. So I take the natural log of both sides. So now I've got the natural log of 100 divided by 30.92 equals 0.1171 times t. So I just need to divide both sides by 0.1171. So my time comes out to be, let's do this. Okay. So I take the natural log of 100 divided by 30.92. Then I divide that by 0.1171. And luckily, I get a very reasonable answer, 10. Okay, so looking at my numbers, about 10 years after we started measuring this in 2010, there'll be 100 million. And that kind of fits, right? After in 2007, there was 70 million. So this makes sense, right? So when kind of 2010, right? Because the time is 10, so that's the year is going to be 2010. Okay, did everyone get that on your calculator? Did that work? Awesome. Okay, so the next problem we're going to do, it's money. You could actually do the P times E to the RT. It's really the same thing. And so the setup is I invest $1,000, right? So that's my principal. You could also call it the initial amount. Okay, continuous compounded interest. So I'm going to use E. 3 years. So that means my T is 3. And I have, so this is what I end up with, right? After 3 years, I've got 1,450. And so when they want to know what is the interest rate, you could say I'm solving for K or R. Okay, it's the same thing, right? That I could either say, right? I could say R times 3, or I could say 1,450 equals 1,000. Does it make sense that R is the same thing as K, but we usually use R when we're talking in a money situation? So again, the first thing I do is divide both sides by 1,000. Okay, so I'm going to have the natural log of 1,450 divided by 1,000, which is going to be 1.45 equals R times 3, right? So then I'm just going to divide by 3. So if I say the natural log of 1,450 divided by 1,000, you could also just type in the natural log of 1.45. And I divide that by 3, I get my R equals 0.1239. Okay, so we could say approximately 12.4% interest. Any questions? Okay, so kind of we started with the kind of the money situation, but now we see that formula covers so much more than just interest rate of money. Okay, it covers anything that's continuously growing or decaying. And something that grows or decays, you could think of as heating and cooling situations, right? So that's what's happening here. I've got someone takes the cake out of the oven, and we're using Celsius, so it's a 180-degree oven. And then they put it in the refrigerator, which is 3 degrees Celsius. After 10 minutes, the cake has cooled to 150 degrees Celsius. The temperature of the cake T minutes after it's removed from the oven can be modeled by this equation. So the only reason it's not the basic equation, the reason it's got the +3 in there, is the temperature inside the refrigerator doesn't go below 3, right? So they're not just, they're going to have it, go to, kind of time continuing, right? The initial heat has dissipated, but it's not going below 3, right? Because the temperature, we're all good while we're adding 3 in this situation. Beautiful. The other thing for this A, which is like A sub 0, right? A or A sub 0, the initial temperature of the cake when we pull it out of the oven, does it make sense? It's 180 degrees if it's been sitting in the 180-degree oven. Okay, so our A is going to be 180 degrees. Bless you. Okay, I'll be able to find K. That's the only thing I don't know in this equation, right? So if I take this, right, the temperature after the 10 minutes is 150. The A is 180 times e to the K times the 10 minutes plus 3. So I've got, it's kind of slightly ugly looking, right? But I've got an equation. The only thing I don't know is K. So I can solve for K, right? Even though it's stuck up in the exponent. So the first thing I do is I subtract 3, because this is why we practice those steps, right? In Tuesday's lesson, I subtract 3. So now I've got 147 equals 180 times e to the K times 10. So now I divide both sides by 180. Okay, so now I've got 147 divided by 180 equals e to the K times 10. What do I do now? Beautiful. I take the natural log of both sides, because this lets, now this side is just going to be K times 10 equals the natural log of 147 divided by 180. So I'm going to divide both sides by 10, and I'm going to be able to find this K. Then we're going to use that K to figure out how long, what the temperature is going to be after 45 minutes. So you don't want to get rid of that K too fast. Okay, so I say natural, I'm going to put this so you can see it a little better. Okay, I say natural log of 147 divided by 180. Okay, and then I divide that by 10. Okay, so did we get negative 0.02? Okay, I'm going to store this, just, I'll pick a different letter. I'm going to store this value. I'm going to pick my favorite letter, J. Okay, so I've got that stored because now I want to figure out the temperature of the cake after 45 minutes. So I'm going to say, what's the temperature after 45 minutes? And it's going to be that initial 180 times e raised to this K value, right, which is about negative 0.02 times 45, right, plus 3. Okay, but I'm actually going to use my stored value. So I say 180 times e to the, I stored mine as J times 45. Okay, and then I am going to add the 3. Okay, so did you guys get 75 degrees, like 75.3 degrees? Okay. Questions on that? Okay, so far so good. So what we're gonna do now is you're gonna do assignment 8A, which we'll take a look at now.